So we're going to start with the problem of the week. In case you didn't see on the website, I'll give you a moment to read it. And feel free to type any ideas in the chat. Okay, so does anybody have any ideas? Yeah, so probably the first thing to notice is that this question doesn't seem doable with only trigonometry because we're raising cosines to really large powers that probably won't work very well. So what we're going to do instead is, as some people have mentioned in chat, we're going to try using complex numbers. So let omega be equal to e to the I pi over 2019, which is a 4038th root of unity. So can anybody tell me what omega plus 1 over omega is? Feel free to type in the chat. Yeah, it's going to be 2 times the real part of omega, which is in this case the cosine of pi over 2019. So it's going to be 2 times the cosine of pi over 2019. And we can generalize this for omega to the k, namely omega to the k plus 1 over omega to the k is equal to 2 times cosine pi k over 2019. So we can write it in this form. So with this form, we can just plug it right back into our original expression to get that the sum can be written as 1 over 2 to the 2020 times the sum from k equals 0 to 2018 of omega. Oops, that should say omega to the k and 1 over omega to the k. To the 2020, which is equal to 1 over 2 to the 2020. And then now we just expand with geometric, we just expand with the binomial theorem. So that's 2020 choose I times omega to the k times omega to the k times 2020 minus I over omega to the ki. Does that make sense? So yeah, there's a typo in the first sum. It should be omega to the k plus 1 over omega to the k, not omega plus 1 over omega. Okay. So moving on, we now have a double sum. So in general, when we have a double sum, we're gonna try reversing the order of the summations to see if we get anything nicer. So in this case, this works. If we simplify and sum swap, we're gonna get 1 over 2 to the 2020 times sum from I equals 0 to 2020 of 2020 choose I times the sum from k equals 0 to 2018 of omega to the k times 2020 minus 2I. So does anybody know how to evaluate the innermost sum now that we've sum swapped? Yeah, so the form looks a bit strange, but if you notice, the only thing we're varying is k in the sum. So actually, this is just a geometric sequence. So note that omega to the 2020 minus 2I is equal to omega squared to the 1010 minus I, and omega squared to the 2019 to root of unity. So this number is as well. So now if we evaluate the geometric series, we let z equals omega squared to the 1010 minus I. And then what we want is just sum from k equals 0 to 2018 of z to the k. So this becomes, by the formula for geometric sequence, z to the 2019 minus 1 all over z minus 1. And remember that z is a 2019th root of unity. So the top is going to always be 0. So we get that this is equal to 0 unless z is equal to 1, in which case we can't use the sum of geometric sequence. So if we look at the sum as a whole, this means that basically all the terms are 0 unless the exponent, unless unless z is equal to 1. So if z equals 1, then the inner sum just becomes 2019. So our answer is just 1 over 2 to the 2020 times 2020 choose 1010 times 2019. And it's 1010 because z is equal to 1 when I is equal to 1010. So now we're basically done. We just need to extract the answer. Remember that we wanted the numerator mod 1009. So the first thing we need to do is find the numerator. Note that the denominator is some big power of 2. So we're going to first try to find the number of powers of 2 in 2020 to 2010 times 2019 so we can find the numerator. So using some standard tricks, we just get that there are 2013 powers of 2 which divide 2020 factorial, and 1003 which divide 1010. So 2020 choose 1010 has 7 powers of 7 factors of 2 in it, and 2019 has 0. So the numerator is 2019 times 2020 choose 1010 all over 2 to the 7th. So 2019 is equivalent to 1 mod 1009. So it suffices just to find 2020 choose 1010 mod 1009. So as someone said in the chat, we can use Lucas's theorem, or we can just expand the numerator. So 2020 factorial is going to be the product of all numbers from 1 to 2020 1 to 2020, and we can group them as such. We have 1008 factorial times 1009 times the product of 1010 through 2017, and then the product of the last 3 terms. So the reason we do it like this is that we want to find it mod 1009. So the first thing we need to do is cancel out the 1009s, because 1009 is prime, and once we do that, we can just use normal modular arithmetic. So the denominator is going to be 1010 factorial, which is squared, which is 1008 factorial squared times 1009 squared times 1010 squared. 1010 squared is equivalent to 1, and the 1009s cancel out with the 2 1009s we extracted at the top. So the first 1009 cancels, and the second 1009, which is part of 2018, cancels out to 2. Aditya. Sorry, we're having some technical difficulties. Yeah, okay, so after canceling out the 2 1009s, we're left with 1008 factorial times the product of 1010 through 2017. But each of these numbers, if we take them mod 1009, we get 1 times 2 all the way to 1008. So this second group is also 1008 factorial. So the numerator is just 1008 factorial squared times 2 times 1 times 2 all over 1008 factorial squared, which is 4 mod 1009. So our numerator mod 1009 is just 4 over 2 to the 7th, which is 1 over 32 mod 1009. So this can just be easily computed to be 473, and that's our answer. So the modular arithmetic part at the end is a bit tricky, but the main takeaway is supposed to be the beginning since our last class was on trig and complex numbers. So are there any questions? So I'll just say as a note, the sum swap we did during this solution was actually unnecessary. If you're familiar with the roots of unity filter, you can just proceed to the answer in one step. So you can try that on your own after class. But if there are no questions, we'll just move on to today's topic, which is on Euclidean geometry.
Okay, so we're gonna get started with our topic for this week, which is geometry. So here is our first problem, which is just like an introduction to basic geometry. Right, so I'll give you guys a bit, and if you guys have suggestions or ideas, you can put them in the chat.
Oh, and in general, many of for our slides, we're only going to have the diagram on the first page. So we recommend you draw it on your own scratch paper to follow along.
Yeah, so, well, before we get to similarity, what triangles do you see are similar? Yeah, so I think that's a big jump in logic for now, but basically what we see is that K is the midpoint of both segments AC and MP, right? So essentially, we have that it's a parallelogram, right? And here's like another way of seeing it. You have those two equal sides and you have two equal angles by vertical angles, right? And so either way, you get like these congruent triangles in a parallelogram, right? So what this tells you is that, well, if it's a parallelogram, the opposite sides are parallel, right? So in particular, it tells you that CL and AM are parallel, right? So, well, now how do we proceed? Where do we go from here? So our goal is to find um, the length of LP, right? And so how would we, and so, well, we want to somehow be able to relate some lengths to other lengths, right? So if now that we have these parallel lines, we have these similar triangles, right? So we want to somehow be able to take advantage of these similar triangles, which leads us to want to find the ratios of sides, right? So in particular, we see that CL is an angle bisector, right? So what this tells us is by the angle bisector theorem, we have the ratio of AL to LB, right? Because what the angle bisector tells us what the angle bisector theorem tells us is that AL to LB is equal to AC to CB. Right, and both of those lengths are given, so that's 3 to 2. Right, so now that we have this, right, yeah, the diagram is pretty useful for this week in general, because we're like, the diagram's only going to be on the first page, right? So be sure, like, it's a very good idea to copy it down. We could go back to the diagram to give you guys a bit more time, but yeah, so here's the diagram. Yeah. So, but now the idea is we have AL to LB is 3 to 2, right? As we just said. And we're given AM and we want to find LP, right? So from here, we should have all the information that we need because we have those two similar triangles, right? In particular, BLP is similar to BAM, right? And well, we can find the ratio of these triangles to be 2 to 5, right? Because we already knew, we knew BL to LA, and so this is just BL to BA, but BA is BL plus LA, right? So that's how you would find the ratio of the triangles, and then from here it's just multiplication, I guess, because you already know AM. So LP is just 2/5 of AM. Right, so that would be how you would get your answer of 72. Right, so does anyone have any questions on that? If not, I guess we can move on to our next question. So here's our next question. So again, I'll give you guys a bit to think about it and then send ideas in the chat. Also, remember to copy down the diagram if you haven't already. All right, so I guess we're going to, so we want to interpret what the question means, first of all, right? Like, for example, in particular, what does that condition of, you have these two parallelograms, ACDF and ABDE, right? So you have the A, they're both parallelograms, and B, their areas are the same, right? So now, what, like, this is pretty big information, right? Yeah, exactly. So you get that CAD and BDA, which are each half of their respective parallelograms, therefore must have the same area, right? So here we're going to be using brackets to denote area in case you are not familiar with that notation, right? But like, so we have these two equal areas, which basically means, well, since the bases of these two triangles are the same, that means B and C have to be the same distance from these bases, right? So in particular, this tells us that these two sides, these two lines, AD and BC, are parallel, right? Because if they're the same distance from the line, then they have to be parallel. Right. So that was useful, right? That was a good interpretation of that information from the problem, right? But now we want to actually start calculating some things, right? We want to use, like, for example, this other condition that AG, AGB has an area 10 greater than CGB, right? So, well, how would we try to use this, right? Why does ABD equal ACD, like their areas? Because the area of ABD is going to be half of the area of the parallelogram ABDE, right? And the area of ACD is going to be half the area of the parallelogram ACDF, right? So yeah, um, yeah. Basically, they're just half of their respective parallelograms, right? So now we want to use this other information that we were given, right? Which was that that AGB has an area 10 more than CGB, right? So the best way to, or at least the easiest way to take advantage of this is to just set variables to things, right? So in particular, we can let x equal the area of CGB, and then that makes the area of AGB x plus 10, right? And now we're going to start trying to calculate things in terms of x, right? So in particular, we're going to look at DGA, right? So, well, what can we say about the area of DGA in relation to other or in relation to, in particular, the areas of CGB and AGB, right? So, in particular, well, it's really nice if we can really, so the area of triangles are really nice, um, especially when the two triangles share something in common, right? So like in this case, it would be like DGA. The reason why we're considering DGA is because, well, DGA and AGB share the same height, right? So that would be really nice to take advantage of, right? So, well, we can find the ratio of their areas, because then the ratio of their areas is just the ratio of their bases, right? So what this means is that the area of DGA is DG over GB times the area of AGB, right? Does that make sense? And now we already know the area of AGB. The area of AGB is just x plus 10, right? And DG to GB, well, we remember that AD and BC are parallel, right? We just found that. Right, so what this means is that, well, DGA and BGC are similar, right? So that means that DG to GB is going to equal AG to GC, right? But, well, what do we know about AG to GC? AG to GC is actually the ratio of the bases of the two triangles that we already know, AGB and CGB, right? And we see that those two triangles also just have the same height, right? So in particular, we see that the ratio of AG to GC is just x plus 10 to x, right? DG to GB equals AG to GC. Because we have these two parallel lines, AD and BC, right? So yeah, DG. No, no, no. We have DGA is similar to BGC. Because we have BC, basically just angle similarity, right? Because we have parallel lines and then we have two transversals, right? And this always just makes similar triangles, right? Like in particular, like BCG, angle BCG equals angle GAD, and CBG equals GDA, right? Yeah, so that's just information that you can get from the parallel lines, right? So that gives you that nice relation of ratios, right? And so now we can express the area of DGA in terms of x, right? So now, why is this useful, right? Well, it's useful because DGA is actually relevant in one other way, right? Because DGA, if we look at it, if we add the area of DGA to the area of BGA, well, then those two areas should add up to the area of BAD, right? You're just putting those triangles next to each other, right? And well, the area of BAD, we already know that area actually, right? Because that area is just half of the area of ABDE, which is known, right? So that's really useful, right? Because now we have an equation in terms of x, right? We have this x plus 10 plus x plus 10 squared over x on one side, and then 84 on the other side, right? So, well, now we just solve for x, right? So we'll simplify the equation, right? And then we'll get this quadratic in terms of x, right? X squared minus 27x plus 50 equals 0, right? So what this means is, well, we can just solve this quadratic, right? So we can factor it as x minus 2 times x minus 25 equals 0, right? So this tells us that x is either 2 or 25, right? So uh, now we're going to, we remember that we want to minimize the area of the whole hexagon, right? So we'll begin by just considering this top half of ABCD, right? So what is the area of ABCD? Well, it's the area of ACD plus the area of ABC, right? And all of these areas we know, right? Because uh, ACD, we see that it is half of the area of ACDF, right? It's half that parallelogram again. Right? So that's the area of ACD, right? And the area of ABC we also know, right? Because the area of ABC is just the area of AGB along with the area of CGB, right? And those are x and x plus 10, right? So we can actually express the area of ABCD entirely in terms of x, right? So now we think about it, and well, we want to try to minimize areas in general, right? So because the question asks for the minimum area of A, B, C, D, E, F, right? So well, what this motivates us to do is to consider the x equals 2 solution, right? So well, if we let x equal 2, then the area of A, B, C, D is at least 98, right? if x were 25, it'd be more than 98, right? So, but now we want to relate ABCD to this whole hexagon, right? And well, again, we'll take advantage of this of the fact that we have a lot of symmetry in this problem, right? Because of these parallelograms, right? And in particular, like let's yeah, so um we do so we do have equalities like that, but we actually have a lot more equalities, right? Because if we look at it, this whole diagram, like if we consider just the midpoint of AD, right? That midpoint, uh, everything should be symmetric about that midpoint because we have these parallelograms. Because both parallelograms are symmetric about that midpoint, right? So that means that all 6 points have to be symmetric about that midpoint, which means that A, B, C, D, and D, E, F, A are symmetric about that midpoint as well, right? So what this tells us is that they have the same area because they're symmetric, right? So this is now basically the whole problem because we already know the area of ABCD, right? So, and what we just found was that, okay, so the last step is, so we consider the midpoint of AD, right? So we claim that this midpoint is special, right? And what we mean by that is, well, it's the midpoint of one of the sides of a parallelogram, right? For example, ABDE, right? It's the midpoint of one of its diagonals, right? Which means that the other 2 points have to be symmetric about it as well, right? And this holds for both parallelograms, right? We have that B and E are symmetric about this midpoint, and we have that C and F are symmetric about this midpoint as well, because of those 2 parallelograms, A, C, D, F, and A, B, D, E, right? So this tells us that just A is symmetric about, A and D are symmetric, B and E are symmetric, C and F are symmetric, right? So this tells us that the whole trapezoid ABCD is symmetric with the whole trapezoid DEFA, right? So that this means that they have the same area, right? And we already found the minimum area of ABCD was 98, right? So the minimum area of DEFA is also 98. And so the minimum area of the whole hexagon is just their sum, which is 196. So does anyone have any questions on that? If not, I guess we'll move on to Aditya with trigonometry.
Yeah, so I guess we'll start with some basic review. And so if you have a right triangle ABC, then the sine of angle B is defined to be AC over BC, and the cosine is defined to be AB over BC. And likewise, the tangent is just sine over cosine, so AC over AB. And so the way that we normally define them is with the unit circle. And so we can use, so we can extend these definitions for all of the angles on the unit circle. And so the main ideas that we're going to be using in the following problems is the law of sines and the law of cosines, which are very important identities. So the first is the extended law of sines. And so this just says A over sine A equals B over sine B equals C over sine C, and that's all equal to twice the circumradius. And then we also have the law of cosines, which just says A squared equals B squared plus C squared minus 2BC cosine A. And you can see that this reduces to so you can see that this reduces to A squared equals B squared plus C squared when angle A equals 90 degrees. So, so with that, we'll get started with our first problem. So I'll give you all a moment to read this one over and try to copy down the diagram. Okay, so let's get started. So a lot of you were saying in the chat to try using the law of cosines. And so the first thing we need to use the law of cosines is like some angles here. And so we know APB equals BPC equals CPA. And so they all have to add up to 360 degrees. So that immediately gives that they're all equal to 120 degrees. And so given this, the problem already said that AP is 10 and BP is 6. And we have the angle between them, APB is 120 degrees. So we can just use the law of cosines as suggested to find the value of AB. And so AB is 6 squared plus 10 squared minus 2 times 6 times 10 times cosine 120. And so that comes out to 196. And that means that AB is 14. So right now we don't have any information to find more lengths just based on what we have right now. But the last idea that in the problem was that the problem also said that B is a right angle. So that means we know AB squared plus BC squared is AC squared. So the idea we're going to use is set a variable for PC and use the law of cosines to find AC and BC, and then use our final relation AB squared plus BC squared equals AC squared. And so if we start, we will just let PC equal X. And from the law of cosines on PBC, we know that BC squared is 6 squared plus X squared minus 2 times 6 times X times cosine 120. And if we simplify that, that's X squared plus 6X plus 36. And we can do the same thing for PAC. And so that just gives AC squared equals 10 squared plus X squared minus 2 times 10 times X times cosine 120. And that's X squared plus 10X plus 100. And so since angle B since we were given that angle B is a right angle, we know that so we know that AB squared plus BC squared is equal to AC squared. And we already have all of the values in this, so we can just substitute. And so we have 196 plus x squared plus 6x plus 36 equals x squared plus 10x plus 100. And so this is just a linear equation, and we can just find what x is. So x comes out to 33 in this case. So does anyone have any questions? Okay, so I guess we'll move on to our next trig problem. Or I guess this one may not necessarily be completely trig, but it's using the same basic geometry ideas. So I'll give you all a moment to read and draw your own diagram. So did everyone get a chance to read this one over and draw a diagram? Okay, I'll take that as a yes. So does anyone have any ideas for how to get started? So in our diagram, we've actually marked a point Q as the intersection of OP1 with omega1. So if we just look at this, O is going to be so we've let O be our center of the equilateral triangle. And so this is because we can try to utilize some symmetry with the equilateral triangle. And so the main idea here is that we know that OP1, P2 is going to be a 30-degree angle because it's 1/2 of the 60-degree angle in the equilateral triangle. And so the reason that this is good is because we know that P1, P2 is tangent to the omega1 circle. So that means that if we have the angle OP1, P2, then this is the same as the angle Q1, P1, P2. And so with that, we could use the inscribed angles theorem to find what P1, Q1 is. And so if we just start, we have So as I said, we know that OP1, P2 is 30 degrees. And so we're just going to let OP1 intersect omega 1 at some point Q1. And so the reason we're doing this is basically what I said. We know that P1, P2 is tangent at P1. So we want to sort of relate that. So we can draw Q1 so that we can use our angle relationship to find what P1, Q1 is. And so because of the inscribed angles theorem, OP1, P2 is equal to Q1, P1, P2. And because of the theorem, it's 1/2 of Q1, O1, P1. So, and since OP1, P2 is 30 degrees, we just have Q1, O1, P1 is 60 degrees. And since the radius of all three of those circles was 4, this just means that it means that P1, Q1, O1 is just an equilateral triangle with side length 4. O1 is so we're just letting O1 be the center of omega 1 here. And so if you see here, so OP1, P2 is the same as Q1, P1, P2 by the way we defined it. And so Q1 is on the same line as O and P1. So that means that O P1 P2 should be equal to Q1 P1 P2. And because so we know that the problem says that P1 P2 is actually tangent to omega 1. So that means that we can use the inscribed angles theorem and say that the arc that's subtended by that angle is actually half of the central angle, which is P1, O1, Q1 in this case. So that means that Q1, O1, P1 has to be twice OP1, P2, which means that it's a 60-degree angle. Yeah, we can, yeah, you can also think about it that way, but yeah, so it's the, yes. So, okay, so now that we have a 60-degree angle, and so that just means that Q1, O1, P1 has to be an equilateral triangle because OQ1 and OP1 are both radii of the circle. And so P1, Q1 has to be the same as the radius, which is 4. And so does anyone have any idea for why this could be useful, the length of P1, Q1? Yeah, so power of a point. So if we go back to our diagram here, if we could find, so our end goal is to find the side length of the equilateral triangle, which, so if we find what the value of OP1 is, then that would be enough because we can just use properties of 30, 60, 90s to find the side length of the equilateral triangle from the distance from O to P1. But so given that P1 Q1 is 4, we can try to use power of a point to find the length of OP1. So how do we use power of a point here? We need another so if we let OP1 equal to x, we know the power of a point is we know the power of a point is supposed to be OQ1 times OP1, which is just x minus 4 times x. But we need another way to relate, so we need another relationship so that we can actually solve for the value of x. And so what we're going to do is we've marked x as the point of tangency between omega 1 and omega 2. And yes, so if we draw the line OX, we can, so OX will be a tangent. And so that means that the power of a point, the power of O with respect to omega 1 is actually just OX squared because OX is tangent. And so now it remains to figure out what OX is. So does anyone have any idea for what OX is equal to? So O is basically just the center of this whole diagram. And so if you look at the tangency point between omega 1 and omega 2, you know that OX has to be, so it's basically by symmetry that OX should be tangent to both of the circles. But another way you can think about it is that O1 and, so if we let the center of omega 2 be O2, then O1, O2, and X would be a straight line. And O1 XO has to be equal to O2 XO by symmetry, and both angles should add up to 180 degrees. So they both have to be 90-degree angles. So yeah, so that means it has to be tangent. So we know that O1 XO is equal to 90 degrees, but do we have any other angle relationships that we can use here to find the value of OX? So actually, we can say more about this diagram. We can say that O1 OX is a 30, 60, 90 triangle. And so the reason for that is that so if we just yeah, so yeah, that works. So if you just so as the person said in the chat, if you just consider the triangle formed by the 3 centers of the circles, the center of that triangle, so that triangle is equilateral, but also the center of that triangle is O, and that's just by the same symmetry argument. And again, by symmetry, we know that O1XO has to be 1/6 of the angle, the central angle at O. So it's just 1/6 of 360. So we can say that O1OX is a 60-degree angle by symmetry. And so because we have this symmetry argument that gives what O1OX is, and we also had the other argument that gave O1XO is 90 degrees, that just means that this is a 30, 60, 90 triangle. And since the length of OX is 4, we can say the length from, so we can say that so since O1x is 4, we can say that OX equals 4 over root 3. And since the power of O with respect to omega 1 is OX squared, the power is just 4 over root 3 squared, which is 16 over 3. And so now this power is also equal to OP1 times OQ1, because that's what we said earlier. So if we just let x equal to OP1, then OQ1 is x minus 4 because P1 Q1 is equal to 4. And so now we just get a quadratic equation for x because because both of these are relations for the power of O. And so x times x minus 4 has to equal 16 over 3. And we can just solve this quadratic equation. And so if we use the quadratic formula, we'll get x is 2 plus 2 times the square root of 7 over 3. So does anyone know how to finish from here? So we know what OP1 is, and we just want to find the area of the triangle. Yeah, so we could just find the side length of the triangle, which is actually just going to be x times root 3, or we can look at it in a different way, and we can just separate the area of P1, P2, P3 into 3 times the area of P1O, P2, because P1O, P2, P2O, P3, and P3O, P1 all have the same area. And so we have 3 times the area of P1O, P2, and for that one, we'll just use our half AB sine C formula. And so that gives 1/2 times OP1, which is 2 plus, so we'll just, yeah, so it's just 1/2 times OP1 times OP2 sine 120 degrees, but OP1 equals OP2 by symmetry. So that means that our final answer is just 3 root 3 over 4 times OP1 squared. And so we can just evaluate that to be 10 root 3 plus 6 root 7. And so to get it into our right answer format, that's root 300 plus root 252, and our final answer is 552. So does anyone have any questions for this one? All right, so we'll move on to our final trig question for today. So does anyone have any ideas for how to begin here? Yeah, so we have this so we have this equal angle here, PAB, PBC, and PCA. And so if we'll just let it equal to theta, then we also know that one way we can relate a trigonometric function to this angle is we can try to use the law of cosines on PAB, PBC, and PCA. So if we do this, then we can first let PA equal X, PB equal Y, and PC equal Z. And if we use the law of cosines on PBC, then we have y squared plus 196 minus 28y cosine theta equals z squared. And so for the other two triangles, you get, we get x squared plus 169 minus 28, 26x cosine theta equals y squared. And z squared plus 225 minus 30z cosine theta equals x squared. So now we have these three equations for x with x, y, and z, and also theta. So does anyone have any ideas for how to try to solve this? Yeah, so we notice that if we add them, we get x squared plus y squared plus z squared on both sides. So this means we can just cancel it out, and so that should say plus one. That should say plus 590, by the way. So yeah, so if we add them and after we cancel out x squared plus y squared plus z squared, if we divide by 2, we just get 13x plus 14y plus 15z times cosine theta equals 295. So now we still have we have cosine theta, but we still have 13x plus 14y plus 15z. So does anyone have any ideas for how to eliminate this term? Yeah. Yeah, so if we notice that if we try using our formula 1/2 AB sine C on the area of PAB, then it becomes 1/2 times 13x times sine theta, and we'll get similar results for the other two triangles. And so we notice if we add all three of these relations, we just get the area of ABC. And so the ABC is a 13, 14, 15 triangle. So you can find that the area of that is 84 through a number of methods. So if we add the areas of the three separate triangles, we get 1/2 times 13x plus 14y plus 15z times sine theta equals 84. And if we multiply by 2, this just gives 13x plus 14y plus 15z times sine theta equals 168. And as someone said in the chat, we can just divide these two equations to get rid of 13x plus 14y plus 15z. And we just get tan theta equals 168 over 295. And so the final answer is just 168 plus 295, or 463. So actually on the handout, there'll be a little bit more information about these points. They actually have a name. They're called Brocard points. And so there's a little bit more information on the handout. So does anyone have any questions? Okay, so that I think Daniel will take over for triangle formulas.
Yep. So our final topic for today is going to be a combination of both the elementary geo we had in the beginning and the trick that we just did. So these problems that we're going to do are greatly simplified with a variety of triangle formulas, which are lots of formulas relating to various quantities that you can find in a triangle. So to start off, I'll just rattle off a bunch of area formulas. So the area of ABC is half base height. It's also half BC sine A. We also have herons. And then we also have inradius times semi-perimeter. Finally, ABC over 4 circumradius. Yep. So does everyone understand what these symbols mean? So we have a lot of shorthand for these triangle formulas. So the side length BC will denote that with a lowercase a. So we'll use a lowercase letter to denote the length of the side opposite of the corresponding vertex. Capital A is shorthand for angle A. S is shorthand for half the perimeter. Small r is the inradius, and big R is the circumradius. The next one we have is the ratio lemma, which allows you to compute the ratio of any segment lying on a side of the triangle, any two segments lying on the side of the triangle, if you know the corresponding angles. So you can prove this with a couple of applications of the law of sines. This is just a often useful formulation of law of sines. The next one we have is Stewart's theorem. Stewart's theorem allows you to compute the length of any arbitrary trivium. It also simplifies a lot if you want to find the length of a median, and we might need this formula later. And you can prove Stewart's theorem by using the law of cosines. You compare a couple of the cosines. And the problems that we're going to do, while they aren't going to be exactly a formula dump that we can immediately solve by bashing it with these formulas, they will be greatly simplified with the use of these. Before we jump into this, let's list off a couple more specialized formulas involving the triangle centers. So we have this diagram down here, triangle ABC. You have the incircle and incenter I. The incircle touches the sides at D, F, and H is the orthocenter. So first off, we have the lengths of the incircle tangents. AE equals AF equals S minus A, and so on. The way you can prove this is you note that AE equals AF by equal tangents. So now you have exactly 3 variables, AE, BF, and CD, say. And then you know that X plus Y is AB, Y plus Z is BC, and Z plus X is CA. So you can solve for them. We also have a couple of the tangents of the half angles. So tangent of half A is equal to R. That should be a typo. We should have R up top. So tangent of half A is R over S minus A. You can prove that just by looking at triangle AIF, which is right. And then finally, some orthocenter formulas, just the lengths of AH, BH, and CH, which are 2R cos A, 2R cos B, and 2R cos C. You can prove this by just using the law of sines on triangle BHC. Are these formulas clear? Yep, the orthocenter is the intersection of the three altitudes. Okay, then let's move on to our first example. Yeah, it's a typo. We flipped the fractions. Yeah, it should be R over S minus A. The orthocenter one, just the law of sines on BHC. Okay, so this is our first AME problem. And I'll give you a bit of time to process this diagram. There are quite a few points. So try to get the diagram down too. So I'll just describe the diagram a little. We're given a fixed triangle. We know one side length and all three of the angles. And then we have a sequence of points that we construct. The midpoints of sides, feet of altitudes, angle bisectors, and so on. And we build up this layer of points, and we're asked to find some quantity about these points. Okay, so let's start working on this problem. So the first thing we know is that the triangle we're given, ABC, we essentially know everything about it. We know all three angles, for example. Since we know A is 30 degrees and C is 45 degrees, then angle B should be 105 degrees. The angles of the triangle add up to 180 degrees. And now, since we know that AB equals 10, if we wanted to, we could find AC and BC using the law of sines. We won't do that right now because we're not sure that we might need that length of the other sides, but we should just keep this in mind. We know everything about this triangle. So how are we going to find AP? It might be helpful to look at the diagram again. Just like, how does AP tie in with the other lengths in the diagram? Yeah, so if we want AP, we're going to need to find AD and PD, say, because there's no nice direct way we can find AP. However, if you look carefully at the diagram, since AH and PN are both perpendicular to BC, we see that we have this set of similar triangles, so that in the AP actually projects down to a nicer segment. So to be more specific, we know that AH and PN are both perpendicular to BC. And we can actually compute angle ADB. Angle ABD is 105, and angle BAD is half of A, which is 15. So that means angle ADB should be 60. Now this is nice. Since PN and AH are both perpendicular to BC, then we see that PDN and ADH are both 30, 60, 90s. So in particular, AH translates a lot more nicely into the length of a segment on BC. So we have a chain of inequalities here, but so AP is AD minus PD. And AD is twice of HD, and PD is twice of ND. So we want twice the difference between HD and ND, which is twice HN. But N is the midpoint of HM, so all we want is HM. The sum of the angles in triangle is 180 degrees. A and C are 30 and 45, so B is 180 minus the sum. Does everything look good up to here? Let me know if you. So you have triangle ABC, right? The other two angles of triangle ABC are 30 and 45. So 180 minus 30 minus 45 is 105. ABC is the central triangle in here. Yeah, well, whenever I use shorthand A, B, and C, they always mean a triangle angle BAC, CAB, ABC. Even if there are other angles coming out of A, because ABC is our main triangle, and so the angles typically refer to the angles of our reference triangle. Does anyone have any other issues up to this point? If not, then now all we have to do is compute HM. So we want the distance between the midpoint of BC and the foot of the altitude onto BC. So it would be nicer if we split HM into two segments, since the midpoint and the foot of the altitude aren't directly correlated. Why 2HN equals HM? N is defined to be the midpoint of HM. M is defined to be the midpoint of MC, so yes. Since it seems like a lot of people haven't gotten down the diagram yet, I think we should just go back up. Just yeah. So we have triangle ABC. M is the midpoint of BC. D is the foot of the angle bisector, and H is the foot of the altitude. Now we define N to be the midpoint of HM, and the line through N perpendicular to BC meets AD at P. And what we want now is AP. Somebody suggested coordinate bash. It should be feasible, but it's a lot easier once we've reduced it to finding HM. Let's jump back to finding HM. So we can split HM into BH plus BM. And we do this because it's easier to compute each of these individual lengths. Now, let's take a look at BH first. While triangle ABH is right, we know the length of the hypotenuse, and we know its angles, so we can find BH. So in particular, BH should be AB times the cosine of angle ABH. Now we know that AB is 10, and ABH is 75 because ABC is 105. So we know the angle and we know the side length, so we can find the length, assuming that we know cosine 75. So it's sine and cosine of 15 and 75 degrees come up fairly often, so it's worth remembering them. You can derive them by just considering angle bisector theorem on a 30, 60, 90 triangle. If you happen to forget the value of cosine 75, you could work around this by computing AC and then using a 45, 45, 90 triangle. On second thought, I don't think that works actually. So you want to know the values of the trig functions of 75 and 15. Anyways, so we can compute BH with right triangle trig. Oh yeah, you can also use cosine sum formulas. The angle bisector the method I mentioned is a geometric way of taking a look at it. And to find BM, we just need BC since BM is half of that. And we can find BC with the law of sines on triangle ABC, since we know everything about triangle ABC. In particular, BC over sine A is equal to AB over sine C. Since A is 45 and C is, since A is 30 and C is 45, we can just plug all of this in and we get that BC is 5√2. That means BM is 5√2 over 2. So now we've computed the lengths of these two segments, and we want to add them together in order to compute HM. And HM ends up being 5√6 over 2. So we square that and we extract our final answer. Does anyone have any questions? If not, then let's move on to our next problem. This diagram is a lot simpler than the last one. So let's get started on this problem. We know the lengths AB, BC, CA, so we know our given triangle. And we also know some angle equalities. In particular, BAD is equal to angle CAE, and BAE is equal to angle CAD. So given this specific set of information, what might we try doing? Does anyone have any ideas on what might we do with this information? Find AD, that would be possible, but that doesn't immediately make use of the fact that we have those equal angles. Since we have a lot of equal angles and all of these angles come from the same vertex, it suggests using the ratio lemma to make use of the ratios on side BC and the angles. They're not triangles that are congruent, they're just angles. BAE and CAD are equal. So the two angles at the top are equal. Actually, since we know that BAE is equal to angle CAD, we also know that BAD is equal to angle CAE. So with this, we can use the ratio lemma. So let's write BE over CE in terms of the angles and lengths that we have. We do this because we know what BC is. So if we know the ratio that E divides the segment into, then we know the lengths of the two segments. So we write BE over CE is equal to AB over AC times sine BAE over sine CAE. And by writing this, we can make use of the fact that we have those equal angles. BAE is equal to angle CAD, and CAE is equal to angle BAD. So we can rewrite this in terms of angles attached to D. So in particular, this is AB over AC times sine BAD over sine CAD. CAD over sine BAD. But now that we have a ratio of sines CAD and BAD, we can use the ratio lemma again to find what this number is. So let's write a second ratio lemma equation. So AC over AB times sine CAD over sine BAD is equal to CD over BD. So just focusing on that first equation, we write another ratio lemma equation. And since we want to find sine CAD over sine BAD, we move everything else to one side. And we happen to know all of these lengths, so we can plug it all in. Does this chain of equalities make sense? We're taking a ratio lemma equation, rearranging it to find what we want. Now, since we know what sine CAD over sine BAD is, we can plug that back in to find BE over CE. So AB over AC is equal to 13 over 14, and we multiply that by 13 over 21. So BE over CE ends up being 169 over 294. Now we know the ratio of BE to CE, and we also know their sum. Their sum has to be 15, which is the length of BC. So now we can solve for BE. If we let CE is equal to 294 over 169 BE, then we can write a linear equation in BE. And now when we solve it, we can get the length of BE, which ends up being 2535 over 463. And answer extraction is 463. Does anyone have any questions? If not, then let's move on to the next question, which is going to be our final problem for the day. So the condition of this problem is very hard to meet, so you should copy down the exact shape of ABC. To start off, let's just define some new points in the diagram. So we know the in circle cuts the median into 3 congruent pieces. And let's just let the endpoints of these pieces be P and Q as shown. So we know that AP, PQ, and QD are all equal. And let's let the in circle touch the sides at X, Y, Z. These tangency points will be a lot more useful later. So yep. So since we know that the median is cut into 3 equal pieces, let's just let the length of all of these pieces be X. So say that AP and PQ and QD are all equal to X. Now we have a lot of lines that intersect or are tangent to our in circle. And when we have lines that cut a circle or are tangent to a circle, that suggests using power of a point. So let's first try power of a point from A. We know that AY squared and AZ squared are both equal to AP times AQ by power of a point. Now AP is X and AQ is 2X. So that means that AY and AZ are both X root 2. And similarly, let's try taking power of a point from D. Then dx squared is equal to dp times dq. And so dx also ends up being x root 2. So now, if we take a look at the diagram, we know that ay, az, and dx are all equal. So we can make a clever observation here. Since bz and bx are equal, and az and dx are equal, that means ab and bd are equal. To make this work, we're going to need to assume that x is on segment BD. So just assume that the diagram looks like the one we have drawn. Then we know that AB and BD are equal. This is because BZ equals BX and AZ equals DX. So we can add these equalities. So when we add these equalities, we get that AB and BD are equal. But BD should be half of BC, which is 20. So that means that AB is 10. So this is good. Not only do we know one side of the triangle, we know another side. So in the end, we want to compute the area of the triangle. And it seems promising to try to find the third side of the triangle and use Heron, because we haven't used a lot of information about the lengths yet. We can write a lot more length equations with the given information. And so we hope that these equations should be enough to solve for the length of the third side. So we need to start using some additional facts about the diagram that we haven't done so yet. So we know what A and C are, where A and C are 2 of the sides of the triangle. And we want the third side, which is B. So let's start off by writing some length equations involving the tangents to the in circle. Sorry, it seems like we're having a couple of technical issues. Oh, okay, we're good now. So now let's write a length equation for dx. Now dx is the difference between db and dx and bx. Now we know what bd is. It's half of a. And we know what bx is, since it's an in-circle tangent. And when we subtract the two, we get that it's just that dx is half the difference between b and c. We know what c is, so we write that dx is half b minus 5. So dx is equal to x root 2. So now we get an equation relating b and x. X root 2 is equal to 1/2 b minus 5. And then we can square that to clean out the root 2. So this is good. By comparing dx, which we related to x, to the sides of the triangle, we get one equation for b and x. We need one more equation in order to solve for it, though. So we can get this by considering the median length formula. We know that AD should be 3 times x, but we can express AD in terms of the sides of the triangle. So this follows from Stewart's theorem, and it's also a useful formula on its own. AD squared should be 2b squared plus 2c squared minus a squared all over 4. Now we know what c and a are, so we can plug that in and find that is b squared minus 100 over 2. But since AD equals 3x, we can put the x into that equation. So 9x squared is b squared minus 100 over 2. This is good. Now we have 2 equations relating x and b. So now the first equation tells us what 2x squared is, and the second equation tells us what 9x squared is. So now x squared is equal to half of half b minus 5 squared. And it's also equal to 1/9 of b squared minus 100 over 2. Why is AD squared equals, so we have the formula 2b squared plus 2c squared minus a squared over 4. You can get this from Stewart's theorem. If you haven't seen this before, it's worth working out on your own time. And since we know what c and a are, then we can plug those values in, and that gives us a single expression in terms of b and constants. So now that we have 2x squared and 9x squared, let's compare them. So now we know that x squared is, from our first equation, half of half b minus 5 squared. But from our second equation, we know it should be b squared minus 100 over 18. So here we're comparing the 2 equations that we have for x squared. And now we have a quadratic in b, and this can be solved. So if we expand everything as a quadratic and then solve, we get that as a quadratic, there are 2 solutions for b, 10 and 26. But we have to throw out b equals 10 because the resulting triangle doesn't satisfy the triangle inequality. It's not a real triangle. The side lengths are 10, 10, and 20, which doesn't work. So we know that b has to be 26. So we know all 3 sides of the triangle now. They are 20, 26, and 10. Now that we know what the triangle is, we can find its area using Heron's formula. When we throw that in, we get that it's 24 root 14. And so answer extraction is 38. Are there any questions about this problem? If no one has any other questions, then that wraps it up for today.
Yeah, thanks for everyone for attending, and we'll get up we'll post the handout and transcript and recording soon. And also the problem of the week will be posted tomorrow at 3.